Hello, my name is Kamal Ali. I'm an independent natural language processing and machine learning consultant. And today I'll be talking about bleeding edge applications of 2020 transformers. So I'll start by just giving a brief introduction about myself. And then I'll talk about the first case study, which is Moxie, a conversational robot for emotional development in children. You can see Moxie on the right there. Moxie is much more than a natural language processing platform, actually. There's been quite a lot of work done in synchronizing its motions. It can rotate and its hand motion to what's going on and what it's saying, both to what it's saying and to what it's being said to it. And my second case study is going to be using transformers for classifying documents as to whether or not the document contains leadership, indicates leadership ability. And then finally, lessons learned from the two projects. Both of these projects were done this year, and they were both done using frameworks and hardware that was only available this year. So we literally could not have done this last year. So I've been in the machine learning space actually since 1987. So I went to the first machine learning workshop, and I got my PhD in 95 from UC Irvine. My PhD was in ensemble classifiers, specifically relational ensemble classifiers. I've done research at UC Irvine, IBM Almaden Research Center, and Stanford University. I have over 30 peer-reviewed papers published in prestigious peer-reviewed journals such as Machine Learning Journal, ICML, KDE, and AI Stats, and I have over 1,000 citations. But I have moved from research now to engineering. I was the lead on the TiVo suggestions engine, and most recently I finished a stint at Apple News as a lead applied scientist there. And now I've been doing consulting. So I'm doing actually consulted along the way for TiVo, Yahoo, and IBM. And I have a book on which I've co-edited on machine learning and astronomy. So let's move on to Moxie. As you can see, Moxie was founded by Embodied Inc., whose job it is to create robots to revolutionize human-centric care. Its founder is Paolo Pergenian and CTO Stefan Scherer. Embodied is a small company out of Los Angeles, and the founders have previous experience in building Roomba and other robots. So I actually do consulting for Fuse Machines. Fuse Machines is a consulting company out of New York, formed by Samir Maski, who is a professor at Columbia. And Fuse Machines, in turn, consults to Embodied. So Fuse has a really clever model. What they do is they're teaching natural language processing and AI to developing countries, principally Nepal. And then the best students, they reach out to them and ask them if they would like to work for Fuse. And so they're able to get really excellent engineers, as well as teaching people in Nepal, as well as being very competitive in their consulting charge rates in the United States. So prior to Moxie, we had in the top right-hand corner, you can see Ivo, the robot dog. Then after that came Jibo, out of Cynthia Brazil's lab at MIT. And the thing with Jibo was, it was compared to things like Alexa and Siri, I think unfairly. And so it wasn't positioned correctly. And because people used it for more mundane tasks, such as show me the weather or what's it going to be like tomorrow in Los Angeles, it kind of suffered from that. So we have a better positioning, I feel, with Moxie. And in the bottom right-hand corner, you can see another application of conversational robots for elder care. So a lot of older people are quite happy to talk to robots. They know they're robots, but they're still happy to do so. and they get a lot of improvement in their quality of life that way. Now, moving on to Pepper in the middle here, the white statuesque robot, you can see compared to Moxie that the first thing that strikes you is the tablet interface. So we have done away with that completely, and it makes it much more natural looking. The eyes are in Pepper are very fake, whereas the eyes in Moxie are very expressive. Moxie also has a much more natural sounding voice compared to Pepper. And part of that is Pepper came out of SoftBank in 2014, and Moxie is coming out 6 years later. And we've had the Transformers revolution in the last couple of years. So we're actually able to do much better voice synthesis and natural language production. Pepper also costs $14,000, almost the price of a small car. And a Moxie is going to cost an order of magnitude less. So here are the differences on the right-hand side. Moxie is more lifelike, it's more realistic, its voice and body language are coordinated, its voice is emotive, the conversation is much more fluid. I will do a demo in a little bit. It's been built on months of interactions in-house. It's cheaper, and it has a much wider range of facial expressions. And most importantly, it is for children. So Moxie is both offering a higher quality product as well as aiming at an audience which will not get tired so easily. So it's very important to have the synchronization between what you're able to offer and what it can do. So now I'm going to show you a brief video of Moxie. Let's look at this.
Hello, Moxie.
So as you can see, Moxie is very expressive and has been very carefully constructed by people in Los Angeles, people with experience in the movie industry and so on, to really have a very engaging set of emotions and movements. So when Moxie comes out of the box, it can have a number of persona. There's a number of curated persona. So for example, Moxie could be a 7-year-old boy. He's shy and cautious, and we have created a fiction that he's from the General Robotics Lab. And the idea is that the child should teach Moxie about the human world. So Moxie is not teaching the child, it's learning from the child. And we're also hoping that it can help autistic children. Autistic children have trouble relating to authority figures, parents, and even peers, but are often quite comfortable interacting with robots. So we really hope that they can be helped by Moxie. Moxie goes through a series of missions with the child, teaching them about emotional lessons, about friendship, how to deal with making mistakes, how to manage your emotion, and so forth. So here are some technical challenges with Moxie. First, there's gaze following. So it's extremely important that Moxie be seen to be looking at you. When you're talking to it, if the other partner in the conversation is not looking at you, it's extremely debilitating to the quality of the conversation. Moxie has to learn to take turns, so it cannot interrupt. And then when it does respond, it should not respond immediately. A machine that as soon as you finish talking, it starts talking back within 0.1 second, it's very unnatural. Humans take time to process before they respond, and we would like Moxie to do the same. It's multimodal, so it's not just natural language. It has its expressions have to match what it's saying, and also they have to match what you are saying to it. So if you say something rude to it, it can have a sad face. If you say something funny, it can laugh, and so forth. Now, since we are aiming Moxie to converse with children, it's super, super important that whatever dialogue it emits does not talk about certain topics. So we have to have a very high recall rate in filtering out these kinds of topics. Longer term, we have other challenges with consistency and memory. So consistency means that if Moxie says to you, oh, I like Star Wars, and then 10 minutes later it says, I don't like Star Wars, that doesn't sound natural, and it will degrade the conversation. So we have to be consistent, and we have to have memory of previous conversations, even across days. So to wrap up, Moxie does automatic speech recognition, as you've seen. It's dialogue-based. It has coordination with its facial expressions and body movement. And it goes through a multi-day curriculum, and it's actually available for reservation right now. So now let's move on to the second case study that I'm going to talk about, transformers for text classification. Specifically, for a document, we need to decide whether or not the document is indicative of leadership capability. I'm going to start by intro to fuse machines. Then I'm going to talk about how difficult it is to actually define what leadership is. As you can imagine, text classification for sentiment analysis is much easier. You look at certain words in the text, they give away pretty much the sentiment of the document as to whether it's positive or negative. But leadership is a much more nebulous task, so it's much more difficult to assess that for a given document. I'm going to then talk about the precise classification task that we decided we should focus on. And then I'm going to talk about some choices we had in terms of representation and learning. What algorithms, what types of representations, and so forth. And then finally, the results that we got. So Fuse Machines is centered in New York, as I said. It has offices in Dominican Republic, UK, and Nepal. Most of its engineers are from Nepal. And the cool thing about Fuse is that it's able to help the developing country as well as use those engineers to be very competitive in its charge rates for consulting in the United States. So it's a win-win situation. So the Fuse Machines team structure typically consists of a PhD or someone with a lot of experience at the top here. Then it will usually have one local AI or technical lead who can also be the project manager, and then a number of distributed engineers, mainly from Nepal. So now let's move on to the definition of the task for this project. The first thing that we noticed for this leadership detection project was the size of the data was quite small. It's on the order of a few thousand documents, each was a few thousand words long. The second thing was as you know, in machine learning, there needs to be a ground truth label assigned to a document. So what we noticed is that before the machine learning project started, this client was doing this manually. So they had all of these documents, and they had created a funnel structure of phases. In the first phase of the funnel, all the documents were poured into the funnel, and each document was examined by 2 lay judges. Not the same 2, but a different 2 for each document. And each judge made their independent decision, and the decisions were then combined and thresholded to make a binary decision, whether the document should proceed or not to the second phase. And then in subsequent phases, the documents were read by expert judges, and the further you go into the funnel, the more judges read each document because they wanted to be very careful about detecting leadership quality. So what we decided was that we would make a classification task as to whether or not the document was good enough to pass phase 1. This was most valuable to our client because phase 1 is where the largest volume of documents is encountered, and as you go further into the funnel, the number of documents decreases and their quality increases. So phase 1 is where they really needed the automation. So we had training data from 6 prior years, but one interesting thing was that the generative function for each year for the ground truth labeling was different. So in earlier years, there were fewer documents, the judges were more lenient, there were fewer judges, and there were fewer phases. So everything was different from year to year. So our training data was actually stratified by year. So we had a choice. Do we predict intra-year or across years? Intra-year would mean that for each year you would build a model and you would take training documents from year X and predict leadership on unseen documents from year X. Or should we build an across years model? An across years model would train from n-1 years and then test it or apply it on the last year. So that's what we decided to do. And that's much more reflective of the actual setting that our client needed. So here is a matrix of scatter graphs. I'm going to focus in on just this one here. Each dot represents a document, and all the dots collectively represent the correlation between Judge A and Judge C. Correlation being how consistent were these judges in judging the leadership quality of a document. What we see is that if they were perfectly consistent with one another, all of the dots would line up along a diagonal axis like this. But in fact, they are very far from consistent. So there was quite a lot of disagreement even among human level judges. And obviously this made us quite worried because we thought, well, if humans cannot decide what constitutes leadership, how will machine learning be able to do so? This column here is a consensus versus Judge A. So you can see on the consensus level, there's at least more consistency. And then the final column is we decided to just randomly have a random judge that just spit out random decisions. Oh, by the way, each decision was a score from 1 to 5 for how leadership worthy the document was. So you can see here that by contrasting the second last column to the last column, the data is not quite random, but it has a lot of noise. So there is still some signal there, and we had to extract that signal. So in terms of representation, how do you represent the document to the learning algorithm? Do you, for example, parse the document, and then there would be various features? This is how things used to be done about 10, 15 years ago. But nowadays, as we all know, we use word vectors. So look at this cat vector here. Basically, each word is represented by a vector of real numbers. And all the different words are represented in this space. This is called the embedding or encoding space. And they have some properties. So for example, this over here, you can see that kitten and cat are close to each other, which in the embedding space, which means they're related and further away from the dog and very far from houses. Also, directions have meaning. So this diagonal direction encodes for gender. You can see as you move from man to, in this direction, from man to woman, you get from the male gender to the female gender. And it's consistent. So for king to queen, it's the same relationship. So this was actually a very exciting finding a couple of years ago. This directionality property existed for word vectors. Within the word vector world, there are many different word vectors. There's one heart, glove, word to vec. Which one should we choose? So we decided to go with the latest, which is the BERT embedding or encoding. BERT is a framework from Google called bidirectional something for transformers. And the thing with BERT is that it's able to encode polysemous words. So words that have multiple meanings. So for example, the word bank in "we were lying near the river bank" will have a different encoding than the same word bank in "I went to deposit money in the bank." BERT also has an advantage that it takes the entire sentence in one go, whereas previously RNNs used to process a word at a time. Now we throw the entire sentence, or in fact the entire document, at Word, and so it can find all the, not only correlations backwards and leftwards to earlier in the sentence, but also forwards and rightwards. There are also other tricks that have been learned in recent years, such as word pieces. So we break up words like happily, we break up into its stem, happy, and the ly, and that way we can learn irregularities involving the suffix ly. We also tried snippeting here to increase the amount of training data. So recall that BERT has a limit of a document length of 128, but most of our documents are thousands of words long. So what we decided to do was to break them into slightly overlapping snippets of 128 words each. In terms of learning choices, here are a bunch of options that have been used for doing text classification over the years, from hidden Markov models, conditional random field, RNN, recursive neural network, LSTM, long short-term memory, and then transformers. Now, since transformers have broken all state-of-the-art, or many of them, benchmarks in the last couple of years, it was a pretty easy decision to go with the transformers. Now, within the transformers world, there are many different architectures. So there are many different variants of BERT, for example. BERT came out of Google, but Roberta is another variant. And then there are these distilled variants. So what the distilled variants do is, whereas BERT has something like 100 million parameters, the distilled variants wonder, could we recode that same information using 6 million or 10 million parameters, relatively small. So distilled BERT and Albert are examples of these compactified architectures. We considered using TensorFlow, the TF, with Keras and K-Train, and we also considered using PyTorch with the Fast AI library on top. We ended up going with Fast AI. It was very easy to experiment with all the different BERT architectures in Fast AI. So in Fast AI, we actually have, for each of these architectures, there's actually a pre-trained model already available. That model may have taken Google many, many GPUs, hundreds of GPUs, and weeks to learn. And what we can do is, after it's finished learning, they make all of those weights, which constitutes that pre-language model, available for everyone to use. So thankfully, we are able to bootstrap off of that, and we get all of the advantage learning that the language model has of the general English language. And then what we do is we pump our specific training data through it, and we fine-tune that model and vary the weights a little bit to adapt it to our specific needs. Now, transformers are normally used for translation or generating another sequence for a robot response, for example. We only needed it to do a classification in this particular application. So we only used the encoder stack. And what we did was we presented the whole document to the encoder. And as I'll show you in the next slide, it goes up through the encoder, and at the very top, it has the most abstract representation of the document. And then we put a softmax layer on top of that to make a binary classification. Actually, it just doesn't emit a binary classification. It emits a score or a probability that the document is a leadership quality document. So here is a somewhat daunting diagram of the general transformers architecture. This was taken from Jay Alamar's Illustrated Transformer, an excellent blog. So the sentence is presented. So basically, there are two stacks. This is the encoder stack, and this is the decoder stack on the right-hand side. The sentence is presented at the bottom, or the entire document, and then it goes through the first encoder. So the first encoder is this green box, which actually has 4 layers or sub-layers inside it. I'm not going to go into detail of all of this, but basically, as you go further up the stack, the neurons or nodes of the network code for more abstraction. There's also a thing called attention, which was very important for transformers. So when you're at the nth word, how much attention should you pay to the n-3 word or the n+7 word, so on. You can pay, so not only are you looking at a particular word, but you're looking at all the relationships between the different words in the sentence. Now for classification, we only need the encoder stack, but when you do have a decoder, you also have attention going across from the output of the encoder into the decoder. So now let me talk about the results that we got for this second case study. We were amazed that we were actually, after a lot of hard work and a couple of months of hyperparameter tuning and search, we were able to achieve superhuman accuracy. That means accuracy better than any of the individual judges by themselves. The accuracy we got was actually equal to that of the consensus of the judges. So if the judges are taken collectively, they are more accurate than any one of them individually. And we were able to match that consensus level accuracy. So that was amazing. Snippeting did not help, which is interesting. So if you recall, snippeting was the process of breaking up the big document into 128 word pieces. And we ended up learning that just taking the first 128 words was as good as snippeting. So what that tells us is, at least for this particular application, just using the first 128 words tells you all that you need to know for leadership, at least for this application and at this level of accuracy. For those of you that know these things, I'm not going to go into a lot of detail. Dropout and normalization both helped. And now, what we did was, instead of delivering a single model to our client, we delivered a series of trade-offs to them. So what basically, in this precision recall curve, if you remember, each model emits not just a binary decision, but a score for each document. So you can sort the documents from the ones that you're the most confident about, the ones that have the highest probability of leadership, to the lowest. Okay, so you sort the documents, and then you look at the subsets of the top 1%, top 3% in terms of confidence. And that generates, depending on where you make that cutoff, it will generate a precision recall curve that you probably are aware of. Precision varies from 0 to 1, and recall varies from 0 to 1. Quickly, precision is, if the model says it's a leadership document, what is the actual probability that it truly is? We can measure that because we have the goal truth labels from the humans, and we can compare the model's predictions to what was the actual goal truth. Similarly, recall, what that measures is, of the total set of leadership documents, how many of them was your model able to pick up, classify as leadership? And typically, by varying the threshold, you get a range of models. So up here, in this precision recall curve, you would get things with high precision. That means we would send to the client a small set of documents, which for sure were, most of them were truly leadership quality, but we may be missing some, we may have low recall in some of the others. So for our application, they actually preferred the high recall and were able to they were willing to sacrifice precision for the higher recall. So this is why it's super important not to take whatever some of these tools have a way of picking the optimal trade-off between precision and recall, but there is no such universal optimal. You have to look at the whole curve, and depending upon what application needs there are, you have to decide where on that curve you want to deliver the model to the client. All right, so I'm going to wrap up with lessons learned. at the start of this project, I really was wondering how useful is this pre-training? How useful is a general model that knows about English but doesn't know anything about leadership, for example? The answer is it's very important. We were, like I said, we were able to get superhuman accuracy just using a few thousand documents because we were sitting on top of these enormous English language documents. I mean, English language models that had been built, the pre-trained models. What worked for us was these excellent machine learning engineers from Nepal. They know the frameworks inside and out. They're great, but they still need direction from someone who has more experience. So by direction, I mean deciding perhaps where to put emphasis, what pitfalls to avoid, and things like that. Just even things that occur, representational choices that occur before even the framework comes into the picture. So this type of combination of having an NLP PhD plus a machine learning lead and a bunch of engineers works really well. Even though transformers and the neural network community would have you believe that you don't need any representational choices, you still do. You don't need as much feature engineering as one used to need for doing natural language processing applications. Like you don't need to know what is a verb and a noun or make semantic sets of cities and countries and so forth. But you still need to do things like deciding what kind of embedding to use, but so there's still some of that. So we got success by exploring hyperparameters, different algorithms, different frameworks. There was a lot of trial and error, which is usual for these applications. But we're still a little bit disconcerted because we cannot explain why it is as accurate as it is. The client was delighted, they were happy, but we cannot say this neuron does this neuron does that. So thank you very much. I also want to thank the team in Nepal, specifically Rinesh, who was the lead, and he's a project manager, Aditya Chapagain, and Sagar Sakota. And thank you very much, guys. These guys, sometimes the electricity would go out, and so they're working under very trying conditions. And what's amazing is, despite all of that, when they actually have electricity, they're able to do bleeding edge world-class work. Thank you very much.